Welcome back to Algorithms and Uncertainty. We've now spent quite some time talking about Markov decision processes with a finite time horizon. Today, we'll turn our attention to infinite time horizons. These Markov decision processes with an infinite time horizon play an important role in reinforcement learning, so maybe you've seen some of the algorithms that we're covering today also in a class on machine learning. Nonetheless, I feel that you should know about them to get an idea of the big picture of Markov decision processes. So let's dive into this and let's first define what a Markov decision process with an infinite time horizon will look like. So again, we have a set of states which we call S. And we have a set A of actions. And then again we have rewards R subscript A of S, which is the reward for taking action A in state S. And then we'll also have the state transition probability. So this is the probability that we move from S to S prime when taking action A. We again have a start state. And we also have policies again. So a policy pi is a function mapping any history which will be S0 to St minus 1 to an action. So again, we will be getting a random sequence of states where we start from S0, then we get into state S1, then we get into state S2, and so on. Here you'll see one important difference, namely we now call the initial state S0 as opposed to S1. When we had a finite time horizon, we started counting at 1, but that's just for notational convenience. What is now the expected reward of a sequence, of a policy? The expected reward of a policy pi is what? Depends, of course, on the state where we're starting from. And this is now the expectation of the individual rewards that we see on the sequence. But we don't have any time horizon, any finite time horizon at which things end. This is why we cannot simply take the sum from t to, well, capital T as before, but we are summing up over all time steps. Now, if we were only summing up the respective rewards that we're getting, then this sum might get infinite. So what we'll do instead is we'll introduce a discount factor. So this gamma, this is somewhere between 0 and 1. And now you see why we're starting at 0, because the first of these will be 0. This is gamma to the power of 0. This will be 1. The second will be gamma. The third will be gamma squared, and so on. And so we are now taking this sum, which actually never ends, which does not end at a certain time horizon, but it just goes all the way to infinity. But because of this discounting factor, this infinite stem will still be converging. So why do we do it this way? Why do we have this discount factor? Well, on the one hand, because we want the sum to be converging, but why does it make sense to have it exactly like this? One way you can think about this is that, well, there is kind of a time horizon because you will stop at some point because, well, in the worst case, you're dying. And this, how is this now captured? Well, we now in each step flip a coin, and if it shows heads, then we continue, and if it shows tails, then we stop. This would mean that we would have a geometrically distributed time horizon. Namely, it is just the outcome of a random coin flip, but this would be exactly what we're getting here. So the first step we're doing with probability 1, the second step we're only doing with probability gamma, the third step we're doing only with probability gamma squared, and so on. Good, so this is how you define this, and the rest is just the same. So again, we have policies, and we again have random sequences of states. Now, what could we do in the context of a Markov decision process with a finite time horizon? We could derive that an optimal policy, which means a policy which maximizes this term, will be a Markovian policy, which only depends on the current state rather than the entire history up to now. And this is true here as well. It gets even easier because in the case of a finite time horizon, we also had to keep track of how many time steps there were still remaining. This is now actually not important because at any point in time, there will always be infinitely many time steps remaining. So even if I do one step, the situation is just as before because there's still the same number of time steps left. Good, so we call the policy Markovian. If the decision only depends on the current state. And there is always a policy, an optimal policy that is Markovian. It's just by exactly the same kind of arguments that we had for a finite time horizon. And how big will this quantity be for a Markovian policy? Let's see. For a Markovian policy, we have that the expected reward that we're getting if we're starting from a state S as, well, this is now what we're getting for the first time step. So this is the action that we are taking in the first time step, plus, and then we would get, of course, the expected reward for everything coming afterwards. But what is this expectation? Well, what we can see here is if we take out this gamma, then we're getting nothing but what we would be getting if we were starting from any state S prime. So then we take this random transition to a new state, S prime, and then we would get the expected reward of the policy from the state S prime. This is exactly the kind of an equation that we also derived for a finite time horizon Markov decision process, where there's one thing that is different, namely here the time horizon doesn't appear anymore because, and this is exactly the point that I was making, this here is nothing but again the expected reward that we're getting if we're starting an infinite time horizon Markov decision process from state S1 of our sequence. And this is multiplied by gamma. Of course, here there's the power of t missing in this term. Cool. So what does this now mean? For v star of s being the maximum over all policies of v of pi comma s, we can of course also write v star of s is equal to how much? What is it that we're getting here? Here we're getting exactly whatever maximizes, whichever action ever maximizes the reward, taking action A from state S plus gamma times the expected reward if we were to start a Markov decision process from here. So we have the same kind of an equation that we had also for finite time horizon. There we had what's the reward of the expected reward of an optimal policy starting from state S if the remaining time is t, and then we had the same kind of an equation, but then the time horizon was reduced by 1. And this is now something that we don't have anymore, so the time horizon is not reduced. The time horizon just stays the same, it stays infinite, but this discounting factor, which was the gamma that we moved out of this expectation here, this is again showing up here, so this is what is also different. But other than that, we had the same kind of an equation also for finite time horizons, and then we used this to implement, for example, our dynamic programming approach. Here in the case of an infinite time horizon, things are a little different, because you cannot just compute, well, where would you start computing these v star values? This will actually now be the much more involved thing that we'll have to be talking about today. But this equation will still be extremely important, and it is called the Bellman equation. Named by the researcher who introduced all these Markov decision processes and who also actually observed that an optimal policy is always Markovian. Good, so what's our plan for today? Our plan is, how do we now compute an optimal policy? How do we get there? And the idea is, and this is the first idea that we're taking, try to compute this v star of s. Well, this is something that we cannot do just as easily recursively as before, but there are still a number of ways to do this. There is one way. The first way that we'll be seeing is via linear programming, and then we'll also see a dynamic process which converges to this v star. We now want to compute an optimal policy for such a Markov decision process with an infinite time horizon. How do we do this? Well, our key observation is that we will actually only have to find a solution to this Bellman equation. Once we have a solution to this, then we are done. Or, and this is the first thing that we'll be doing now, we will show that if we have a vector such that we now want to compute an optimal policy for such a Markov decision process with an infinite time horizon. How can we do this? Well, our key observation will be that all we need to know is these v star values, because from the v star values you can infer what the policy looks like, the optimal policy. This is, by the way, not really surprising, because this is something that you usually do when you, for example, solve a problem by dynamic programming. Then, by only figuring out the values of the optimal solution or of the partial optimal solutions, you immediately also know what the optimal solution looks like by just tracing back how things came together. Now here things are not as obvious, because it's not just a recursion which just ends somewhere, because we have the v star appearing here and here. But nonetheless, the same idea still works. And we will state this now a little more generally, so that we can also use this to compute approximately optimal policies, which we will be doing afterwards. Namely, let's show the following lemma. Let Ws for all states S be a vector such that the difference of Ws and v star of S is no more than epsilon for all S, which means that our Ws here is close to this v star of S. Then the policy pi defined by the action that we choose in state S should be one of the actions that maximizes Ra of S plus gamma times the sum of all S prime in S, P of S, PA of S, comma S prime, W S prime. And this policy fulfills V of pi comma S is at least V star of S minus 2 epsilon over 1 minus gamma for all S. So, what does this tell us? Let's now assume that we have this vector W, such that each component is close to V star of S. So the component WS is close to V star of S. Then, let's define the policy by, well, pretend that these were the actual V star values, and just take the action, whatever action maximizes this thing here. Then this policy has an expected reward of at least the optimal policy's expected reward minus something, which will be smaller for smaller epsilon. So this is this epsilon here. So in particular, let's talk about epsilon being 0. Then WS and V star of S are exactly the same. So this policy here, which tells us take always the action which maximizes this right-hand side, this will be an optimal policy, because here we have V of pi comma S is at least V star of S. Good. So this tells us that eventually all we have to know is such a W vector. Let's prove this. It's actually pretty easy to prove it. Namely, what we'll do is we will let S hat be the state S, for which WS minus V of pi comma S is largest. So, W of S, this is an approximation of V star of S. This is what's coming out of this here. Now, our expected reward from state S by this policy will usually not be W of S, but it will be something worse. And this is what we define here. So WS is maybe what we think our expected reward is from state S. If we're looking at this here at the right-hand side, then here, this is what we would be getting by taking action A, if from state S prime onwards we would be getting WS prime. But this is not the truth. We're rather getting V of pi comma S prime. So for which of these states is this the worst difference? Let this difference, the maximum of all these differences, be called delta. And let's now try to bound this delta. What we claim is that delta is at most 1 plus gamma divided by 1 minus gamma times epsilon. What does this imply? This implies that for every state S, we have that V of pi comma S is at least W of S minus delta, which will be W of S minus 1 plus gamma divided by 1 minus gamma times epsilon. And how big is this W of S? This W of S is at least V star of S minus epsilon. So this is at least V star of S minus epsilon minus 1 plus gamma divided by 1 minus gamma times epsilon. And if you now do the math, and if I've done this correctly, then this is V star minus 2 epsilon over 1 minus gamma. So if we're able to show this claim, then this immediately implies our lemma. So how do we show this claim that this delta is no more than 1 plus gamma divided by 1 minus gamma times epsilon? Well, let's have a look at, there shouldn't be a star here, because otherwise this makes no sense. There shouldn't be a star here, because otherwise this isn't defined at all. Good. So how do we bound this delta? Let's talk about this thing here, this v of pi comma s hat. V of pi comma s hat, how big is this? Well, what we're doing is we're getting the immediate reward from action pi of s hat in state s hat, and then we're transitioning to a random new state. And from this point onwards, of course, has to be multiplied by gamma. So we're getting the discounting here. And then we are again starting this policy from state S prime. Now, how big is this here? This here is at least. Let's see, we've defined the delta to be the worst of these differences. So we can now say that this v of pi comma s prime will be at least w of s prime minus delta. And this now means that, maybe let's copy all of this. And let's move out the delta. Delta, what does it get multiplied by? This sum here, this is just the sum of probabilities, which sum up to 1. And then we have this gamma here, so we can move out gamma times delta from this sum. And what about this quantity here? I hope this looks familiar, because in our lemma statement, we said that we are choosing an action exactly so as to maximize this quantity. So what we could do instead is we could instead take the optimal policy's choice. And this will not be better in this sense. Now, what else do we know? Let's again talk about the W of S prime. How big is this at least? W of S prime will be at least V star of S prime minus epsilon. So we might also replace this by v star of s prime minus epsilon. So how much is it that we're getting here? Can again move out the epsilon, and then what this is nothing but v star of s hat minus gamma times epsilon minus gamma times delta. Good. Now this is the expected reward that our policy gets from the state s hat. It's this much. But what else do we have? This quantity here that we've now talked about is, we can also write as ws hat minus delta. So v of pi comma s hat is exactly w of s hat minus delta. And w of s hat is no more than v star of s hat plus epsilon, because the difference between these two is at most epsilon. So if we now plug these things together, we're getting that v star of s hat plus epsilon minus delta is at least v star of s hat minus epsilon times gamma minus gamma times delta. Or this means nothing but epsilon minus delta will be at least minus gamma times epsilon minus gamma times delta. Or, let's see, we can now say that delta times 1 minus gamma is at most epsilon times 1 plus gamma. And this is exactly what we were claiming, that delta is at most 1 plus gamma divided by 1 minus gamma. And so this proves this lemma. Good. So there's nothing super surprising about this proof. It's rather technical. All that we're doing is actually just using these equations that we have and figuring out, okay, these errors that we have, they are just benign in the sense that we are still choosing an approximately optimal policy. Now, what does this tell us? This tells us that all we actually have to know is these v stars, which give us a solution to this Bellman equation. And there's a very easy way to compute them, namely via linear programming. Namely, what can we do? If we wanted to compute these v star of s via linear programming, what we could do is, for example, consider the following. We would want to minimize some of the v star of s subject to Ra of s plus gamma times the sum over all S prime PA of S comma S prime times V star of S prime is no more than V star of S. So and this should hold for all S and A. So the variables in this linear program are these V star values. And now, what is it that we're requiring? We are saying, well, this left-hand side here should never be larger than V star of S. Yes, sure, because V star of S should exactly be the maximum of all of these, taking the maximum over all A. Now, why wouldn't one of V star of S be infinite? Because then this would still be feasible. Well, just check this out. We want to minimize the sum of the V star of S. So, this now tells us that if in any of these inequalities here there's some slack, meaning that there is no state S for which this left-hand side is exactly equal to the right-hand side, then we don't have an optimal solution. Then we could just reduce this V star of S by exactly the slack that this inequality has, and this way we could improve the objective function. So every optimal solution to this LP has for every S 1A making the inequality tight. And this means that the optimal solution corresponds to a solution of the Bellman equation. Cool. So, this is certainly one way to compute the optimal policy. Solve this LP, and then, based on the solution, just trace back what the optimal or how the optimal solution came together. Namely, effectively, it's just find for every state one action that made this tight, this constraint tight. There has to be one because otherwise you don't have an optimal solution. And this will run in polynomial time in the number of actions and the number of states, just because this is the size of the linear program. So it feels fantastic, but unfortunately, this is usually far too slow. And this is why we will next talk about two different dynamics which help us solve or find an optimal policy or an approximately optimal policy much faster, and by iteratively improving an existing policy or an existing value vector. So the first thing that we will now talk about is the value iteration, which works more or less by the same way as solving this linear program, but only approximately so. So trying to find an approximate solution to the Bellman equation, and then we'll use the fact that our lemma that we were proving before also works with approximate solutions to the Bellman equation. Let's now talk about value iteration. What is value iteration? Well, the idea is that we want to find a vector W which is close to this V star vector. And we want to do this by an iterative process. We'll start with just some arbitrary W vector and then we'll keep refining it based on what we know so far. And we do this now as follows. Given a vector Ws, we let T of W be defined by, so we again get a vector which associates a value to each state. And now what we're doing is we'll take the maximum over all actions, so to get what we're getting in the component for state S, and then we'll take RA of S plus gamma times the sum of all PA of S comma S prime times W of S prime. So this is more or less what our what the Bellman equation tells us. If we were looking at the V star values, then this T of V star would be nothing but V star of S. So T of V star of S is nothing but V star of S, because here if we're looking at plugging in here V star of S prime, then this is exactly the right hand side of the Bellman equation. But now we're starting with just some arbitrary vector W, for which this is not necessarily true that it is the solution to the Bellman equation. Probably it is not. Usually we might even start with all W being 0, for example. And now what does this mean? Well, we'll choose the action which maximizes what we're getting from here. So if these were the actual rewards, this would be something good. This would be the best thing to do. But now, as we're moving on, actually in the next step, this won't be the best action, because then these here will again have changed. So to some extent, we're always trying to understand these W's as the estimates of what our policy can give us, but then we are repeatedly improving this policy by always choosing the best of these actions given what we currently think the policy can give us. So one way you can think about this is that this might be initially always a lower bound on what you can get eventually. So this would be at most V star of S prime, and then you're slowly moving up. Then you're slowly improving your policy, and somehow what you're doing somehow propagates through these W values, and they get larger and larger from time to time, because you always realize, okay, actually I can get a little more than what I was thinking before. This T of W, as it is actually kind of doing what the Bellman equation does, is called the Bellman operator. And what we now do is exactly what I was saying. We now start from any W0 and we'll see where we're going. And we'll show the following theorem. for any starting point W0, the sequence defined by W of t plus 1 is equal to t of Wt, so the Bellman operator applied to the previous vector converges to V star. Or more precisely, for every epsilon greater than 0, there is a T star such that for all t which are at least T0, we have that the difference of Ws and V star is less than epsilon for all states. Good, so the idea is that we start from any state and we now see just how our sequence evolves by, we're starting from any vector and we now just see how things improve or maybe not improve, how the vector changes, and eventually we'll get to a point that is close enough to this V star vector. And how do we show this? We show that actually under this Bellman operator, any vectors will get closer together. And this in particular means that any vector will get closer to this V star. So we'll consider the distance of two vectors defined just as the L infinity norm of the difference of these two vectors. So it's the maximum amount that two of these vectors can differ in any component. And now we'll show the following lemma. For any vectors W and W prime, we have that the distance after applying the Bellman operator on both of them is at most gamma times the distance before we were applying the Bellman operator. So let's first prove this. What we'll do is we'll consider any component of our vectors, and we claim, of course, that the mod of the difference in the component belonging to state S is, after applying the Bellman operator, at most gamma times the distance that the two vectors had before. So this has to hold for any state S, because this is what we have here. This is just the maximum over all states of these quantities down here. Good. Let's prove this. Let's now recall how are these things even defined, this T of W and T of W prime. Well, this was exactly using this Bellman operator. So this T of W is written out here, and let's now consider the action that actually maximizes this quantity here. So let A star be an action attaining the maximum in the definition of TW of S. And by that I mean TW of S, recall this was the maximum over all states S. Now let A star be the, it was the maximum over all actions A, and let now A star be the one that actually maximizes this here. Then this is exactly equality. And let's now turn to T of W prime. Well, for T of W prime, there might be some other action which is optimal, which maximizes this right-hand side. So we'll only get that this is an upper bound for W prime. This is an upper bound, of course. Maybe W prime is getting even more than this, because this was actually taking the maximum over all these possible quantities here. Now we're just taking one particular. Now what does this tell us? Let's now see what we have here. We now see that TW of S minus TW prime at the state S is no more than what we have here on the right-hand side. Because this R term is the same for both, and so here we'll only have the difference between these W terms. Now this here is how much? This difference is clearly no more than if we wanted to take the maximum over on any possible states as double prime. How big is now the difference between W and W prime, this S prime, and this is exactly what we called D of W and W prime. So what we have is that this is at most gamma times sum of all states PA star of S comma S prime D of W and W prime. And now this here, this is just 1. Again, we're again taking this sum, which just sums up to 1. Good. So what we're getting here is this is at most gamma times D comma D prime. So we see that this difference here will be at most this distance. And of course, if we're swapping W and W prime, we'll also get that t of w prime of s minus t of w at s will be at most this much. So here, this is entirely symmetric regarding w and w prime. Okay, here, it might actually happen that one of the two is bigger than the other, but we don't know which of the one is bigger. So this is how we're getting here. And in combination, this tells us that actually this also holds for the absolute value. Good. So this proves this lemma. Actually, again, it's nothing super complicated happening here. It is only seeing that after we've applied this Bellman operator, two vectors will be closer together in the sense that the maximum of any difference will be smaller than before. And why can I say smaller? Because this gamma, this is smaller than 1. Remember this gamma, this was the discounting factor. This gamma will be somewhere between 0 and 1. So this is definitely strictly smaller than 1. And this is why what this lemma is actually telling us is that w and w prime will get closer together. And this is actually everything that we need to show in order to show this theorem. Because what does the theorem require us to show? We want to show that now this sequence converges to V star, the sequence that we're computing. Now, all we have to do is consider the distance to V star. And let's then see, okay, the distance to V star actually gets smaller and smaller from time step to time step. Let's write this out. Because if we apply the Bellman operator on V star, then we're getting again V star. This lemma shows that the distance between what we're getting in the tth iteration and V star, this is, it's what? It is, maybe let's do a step in between. It is equal to the distance of, we apply the Bellman operator on what we had before, and let's also apply the Bellman operator on V star. Now this is at most gamma times the distance of Wt minus 1 and V star. And if we keep doing this, then we'll see, okay, this is at most gamma to the power of t times the distance between W0 and V star. And now what we see is that this thing here converges to 0 if t grows large, just because this doesn't depend at all on t, and this here, this goes to 0 for t going to infinity. And this is constant, by that I mean independent of t. So the more iterations we have, the smaller this distance becomes, and this way the W vector gets closer to the V star vector. And this already proves our theorem. Good. So this is actually a very simple analysis of such a dynamic process, namely we show that we are just always getting closer and closer to our fixed point without actually a lot of fancy work here. It's kind of similar to how other fixed point analyses work. Here we can even write this out very explicitly. We can even get a bound on how long does it take until we have what distance to the V star vector. So this of course depends on how far we are starting from this. But this is something that you can do easily here. Nonetheless, what you should also be aware is that we'll never actually reach the optimal V star vector. Well, there's of course the annoying thing about numerical stability, for example, that, well, you won't be doing these computations with finite precision, so this is why this should be good enough, because eventually you won't see any difference anymore, and you should be really careful that you're not jumping around because you are too carefully adapting things. But at least when we're computing with infinite precision, we're converging to this, but we're never actually reaching the point V star unless we started from there. This is maybe not quite true. I realize that we might even get to the exact point, but usually we won't be doing this. Let's now talk about another dynamic way why an iteration to get to the optimal policy, we'll get even to the optimal policy in finite time. And now what we're trying to do is just actually improving our policy from time to time and not improving the W vector, not the value vector. And this is why it is called policy iteration. Let's now talk about a different way to find an optimal policy here, which is called policy iteration. And what is it that we're doing? We are starting from some policy, a Markovian policy, which tells us in this stage, take this action, in that state, take that action, and so on. And now we're trying to improve this policy. And how are we doing this? So we start from an arbitrary policy pi 0. And given pi t, we compute a new policy pi t plus 1. And we do this as follows. We first compute the v of pi t, s for all s. How are we supposed to even compute these? Well, this is actually easy, because this is nothing but a system of linear equations. We have here, if you think back, then we have this here on the left-hand side, and on the right-hand side, we have that this quantity is again defined recursively by the expected rewards that we're getting, depending on the other states that we're reaching. So this is something that you can actually do quite easily. And then what we're doing is we set the new action to choose in state S to be the action that maximizes RA of S plus gamma times PA of S, S prime times V of pi T, S prime. Good. So, by the way, I said this is easy. Well, it's conceptually easy to compute this. It takes a lot of time. This is why such an iteration is much slower than a value iteration. But you can do this. Now, what is happening down here? Here we are now improving our policy. And how are we improving our policy? Well, so far, our policy was getting exactly these kinds of rewards. And now let's improve our policy. And how can we improve our policy? We'll now do something strange, namely, we'll pretend that from the second step onwards, we'll keep using the old policy. But for the first step, we are now doing something smarter, namely, we're choosing the action which maximizes this quantity here. So, suppose you were considering the following policy from step 1, so from the second step onwards, always use pi t. And now, in the first step, choose whichever action maximizes your overall expected reward. And this action will be exactly take the current reward plus gamma times the probability, or the state that you're now randomly moving to, and then from this point onwards, you're getting the reward of this old policy. But this is, of course, not what we'll actually be doing with this policy pi t plus 1, because, and this is what we hope that this policy pi t plus 1 is actually better than the previous policy, in the sense that or how is this different, or how is our reward different from what we have here? Well, here we're actually, or in our policy pi t plus 1, we'll actually also continue using this pi t plus 1 policy also for the following states, or for the following time steps. Good. So our claim is now that this kind of an iteration actually converges to, in finitely many steps, to an optimal policy. So what is it that we are trying to prove when we want to show that this converges in finite time? Well, the thing is, we are only considering any of these pi t or pi t plus 1 will always be a Markovian policy. There might be many Markovian policies, but there are only finitely many. And once we, or what we'll now have to say is that we will never see any of these Markovian policies twice. Because if this is true, it might only be that we see a Markovian policy twice if it turns out to be a fixed point if we're not changing anything. But then this policy is an optimal policy. So this is the first thing to write down. If pi t plus 1 is equal to pi t, then the policy is optimal. Because we have that these values v of pi t comma s fulfill the Bellman equation. More precisely, or stated differently, we could now apply the Bellman operator on this and see nothing changes. So this has to be an optimal policy. Why would nothing change when we were applying the Bellman operator? Because this is exactly chosen such that this quantity here is maximized, which is nothing but what the Bellman operator was also doing. Good. Now, why don't we see any policy twice? So there are only finitely many Markovian policies. So what we'll have to show is that these expected rewards that we're getting will never get worse. And this then implies the convergence, just because we cannot see any policy, or we cannot have a cycle in our iteration. Once we've seen a policy once, we will, and we're seeing a different policy, we won't see this policy again. Good. So all we now want to show is actually this inequality. So let's fix t and show that v of pi t plus 1 comma s will be at least v of pi t comma s for all s. And to do this, we'll define a sequence of policies pi prime 0, pi prime 1, and so on. And how are these defined? Pi prime I is the following policy. In the first I steps, use pi t plus 1. Afterwards, use pi t. So this is exactly the kind of a non-Markovian policy I was talking about before. Now a little more generally, we'll now, in the first I steps, we'll use this policy, and then afterwards we'll use that other policy. And we're doing this only for to prove this inequality. And why that? By this definition, we have that on the one hand, this v of pi t comma s is nothing but v of pi prime 0 comma s. In the first 0 steps, use the new policy. Afterwards, use the old policy. This is exactly the old policy. And we'll also have that the expected reward of the new policy is nothing but take the limit of I going to infinity of vi prime comma s. So therefore, what we want to show is that we have that this sequence of these v of pi prime subscript I is increasing. And this should hold for all I and all s. Because if we have this, then we can keep changing this, or we can keep chaining these inequalities, and then we get exactly what we are requiring here. Namely, this here, this is nothing but the largest, or well, if there were such a thing, the infinite one in the sequence, and it is larger than everything before it, and in particular it will be bigger than the first one in our sequence. Good. So let's prove this claim. And we'll do an induction on I. So what do we now have? In the base case, we'll have I equals 0 or 1, depending on how we state this. Let's say we take this to be 0. Then we'll have that. What is it that we have here on the left-hand side? We have here v prime, v of pi 1 prime comma s. And then we also have the other thing, which is v of pi 0 prime comma s. And what does this mean? How do these two things differ? Here we're doing 0 steps with a new policy. Here we're doing 1 step with a new policy. So this now means that in the first step what we're doing is different. Here we are using the new policy. but only for the first step. Afterwards, we're using the old policy. In this other case, we just use the old policy right from the start. Now, how was the new policy defined? The new policy was defined so that exactly this term here is maximized. I hope you recall this. This is exactly the term that we're maximizing with this new policy. So, what we're getting is that this here is at least this. Meaning that what we're getting for pi 1 prime is at least what we're getting for pi 0 prime. Now, let's move on to, let's keep continuing this proof, and let's talk about a larger value of I. So the induction step will be that I is greater than 0. So what is it that we're now comparing? We are comparing exactly the same kind of quantities, namely v I plus 1 prime comma s. And then we're doing one step with the old, with the new policy. Sure. But then this is not the only step that we're doing with the new policy. We can keep continuing doing steps with the new policy, but only I many steps. Now, similarly, for policy which started at, for which we have only I new steps, so similar argument. And of course here we are now doing only I minus 1 new steps. And now how do these two things compare? What we could now do is we could write the difference of the two. So if we were writing the first minus the second, then, okay, how do these two things compare? This is just the same in both cases. And also this is the same. The only difference is that part. So let's only write that out. We have here v of pi I prime, comma S prime, and then we'll have I minus 1 prime, comma S prime. And how big is this? This here, well, this is something that we already know. This is at least 0 by induction hypothesis. Because this is comparing what the I and the I minus 1 policy are giving us. This is now what the I plus 1 and the I policy are giving us. So this together will be non-negative, which implies exactly what we want, namely that this here is at least this much. And this proves our induction, namely that, what did we show? We showed that the expected reward of this policy, which does I plus 1 new steps, is at least as good as the policy that does only I new steps, and this is true for every state and every I. Good, so what this is telling us is that actually we only keep improving our policy. And in so many ways. We seem to make only one improvement for the first step, but if we keep applying this improvement for all steps, this makes only things better. Because the expected reward, that if we were applying this change to only the first step, then the expected reward is already better than if we were not applying this change. But if we are now applying this change for 2 steps, this can only be even better. And for 3 steps, it can even be only better, and so on. And this means that if we just do this for the entire sequence, the improvement cannot be, or we will have to make some improvement compared to the old policy. And this is why we are not running into any cycle with this policy iteration. Good. So this concludes today's lecture. We've seen 2 very standard ways of computing optimal policies in Markov decision processes with an infinite time horizon. Next time, we'll talk about a very particular problem for which then we could in principle also apply these, but you know it, then the number of states will be again huge. And this is why we'll again talk about the structure of an optimal policy for that particular problem. So this is what we'll be doing next time. I hope you enjoyed today's lecture. As usual, please do let me know if you have any questions. And I hope that you also watch the next lecture. Until then, stay safe. Bye.